Okay, now we are going to look at number 2C. So the equations we were looking at, they were in vertex form. They were in the form of f of x equaling a x minus h quantity squared plus k. And if we look at 2C, we're looking at our quadratic equation, and it is in standard form. It is not in vertex form. So we want to get our equation to be in vertex form, which, if we notice, has this perfect squared quantity. And recall, anytime we needed to create a perfect squared quantity, we needed to use the process of completing the square. So that is coming back again, and that is what we are going to use right now. Now recall, when we go to complete the square, we need the coefficient of our square term to be a positive 1. And in this case, it is a positive 1. So we are good to go. And when we go to complete the square, we're only going to focus on the x terms. We're not going to include the -3. I'm just going to kind of push it off here to the side. And when we complete the square, we're trying to create a perfect square trinomial. So what is that third term that we need to add to the x squared minus 2x to create this perfect square trinomial? So recall, we're going to look at the coefficient of the x term, which in this case is the -2. We're going to take half of that -2, which is a -1. We're going to square that, and we get a positive 1. So we are going to add 1 to the x squared minus 2x. But by adding 1, I've completely just changed that equation. So we're also going to subtract 1 so that we are adding a form of 0. So now, when we go to simplify here, or rewrite this, the x squared minus 2x plus 1, we've created the perfect square trinomial. So that is our x minus 1 quantity squared. And the -1 minus 3 gives us the -4. So now, this and this represent the exact same graph. It's just this one up top here is in standard form. This one down here is in vertex form. So different ways for us to look at our graph, the exact same graph. So we have our vertex form, this x minus 1 quantity squared minus 4, where our a is a positive 1. Right, the a here is a positive 1, which means that our graph is going to be opening upwards. And our vertex, which is the HK, our vertex here is the HK, and our HK here is the 1, -4. So our vertex is the 1, -4. So if we did a quick graph where our vertex is at 1, -4, and our graph is opening upwards, then our graph is doing something like that. Okay. Our domain, we know, can be everything. There's no restrictions on what x can be. Our range is starting at a -4 and going up to infinity, including the -4. Our minimum value is that lowest y value, which is the -4. Max value does not exist because our graph is going up towards a positive infinity. Our interval increasing, our graph is going up as we move across the interval from 1 to infinity. Interval decreasing, our graph is going down, our y's are getting smaller as we move across the interval from a -infinity to that positive 1. Our axis of symmetry, that line that cuts right through the middle of our parabola, goes right through the vertex point. That vertical line, x equal to the x of the vertex, in this case x equal to h or x equal to 1. Our x-intercepts, where we set y equal to 0. So if we have 0 is equal to x minus 1 quantity squared minus 4, we get 4 is equal to x minus 1 quantity squared. We take the square root of both sides. So we're going to get absolute value of x minus 1 is equal to 2. Or plus or minus 2 is equal to x minus 1, or 1 plus or minus 2 is equal to x. So we have an x-intercept at 1 plus 2, or 3, 0, and an x-intercept at 1 minus 2, or a -1, 0. And lastly, we have a y-intercept, when we replace x with 0. So when we replace x with 0, we get 0 minus 1 quantity squared minus 4, or 1 minus 4, we end up getting a negative 3. And my graph is really not accurate if we're looking at the drawing above. Now keep in mind for our y-intercept, when we replace x with 0, we could have come back here to our standard form, and our y-intercept is always going to be our c, because if I replace my x's with 0, I'm always going to end up just getting that c value right there. So I can plug into standard form, or I can plug into my vertex form. But standard form for your y-intercept, it's right there. You don't have to do any work. Okay. Let's look at D. D is a little bit different just because, remember, in order to complete the square, the coefficient of our squared term needs to be, sorry about that, needs to be a positive 1, and our A term is a 2. So it is not 1, which means we're going to have to factor that out in order to complete the square, to create that perfect squared quantity. So I'm going to take the 2 out, but remember, we're only going to focus on the x's. We're not going to touch the 14. Even though it's divisible by 2, we're not going to use the 14. We're just going to push it off to the side. So we're going to factor out that 2. We get an x squared minus 6x, and again, we're just going to push the 14 off to the side because we only want to complete the square on the x's. So now we can complete the square. Remember, we take half the coefficient of the x term, which in this case is the negative 6. And so half of a negative 6 is a negative 3, and a negative 3 squared is a positive 9. But now I have completely just changed that equation by the plus 9 there, but I technically have not changed it by 9. I have really changed it by a positive 18. So in order to keep it balanced, I also need to subtract 18 because I'm on the same side of the equal sign. So I'm technically adding a quantity of 0 to keep the equation equivalent to the original equation. So if we rewrite this now, we have our f of x. What's inside our parentheses, the x squared minus 6x plus 9 is a perfect square trinomial, which we know factors to the x minus 3 quantity squared, and a positive 14 minus 18 gives us our negative 4. So there is our vertex form, the 2x minus 3 quantity squared minus 4. We know that our A term is positive. So because our A term is positive, we know our graph is going to be opening upward. Our vertex is that HK, and in this case, our HK is the 3, negative 4. So our graph, with our vertex being over here at a 3, negative 4, and our graph is opening upwards. So it's down here, lower quadrant 4. Our domain, we have no restrictions, so a negative infinity to infinity. Our range is going from a negative 4 up to infinity, including the negative 4. Our minimum value, our lowest y, is the negative 4. Our max value does not exist because our graph is going up towards a positive infinity. Our graph is going up. Our y values are getting larger over the interval as we move from 3 to infinity. It's decreasing. Our graph's going down. Our y's are getting smaller and smaller as we move across the interval from a negative infinity to the positive 3. The axis of symmetry, that line that cuts right through the middle of our parabola, goes right through the vertex, is that line of x equal to h, or x equal to 3 here. Our x-intercepts, excuse me, as we set y equal to 0, we get 0 is equal to 2, x minus 3 quantity squared minus 4. I bring my 4 over. I divide by 2. I take the square root of both sides. So I get the absolute value is equal to the square root of 2. Because of the absolute value, we get plus or minus root 2 is equal to the x minus 3. And I bring my 3 over. So I get 3 plus or minus root 2. comma 0 for my two x-intercepts. And my y-intercept, keep in mind with my y-intercept, I can look and use vertex form setting x equal to 0, or I can use my standard form. And if I go to my standard form, remember that my y-intercept is always going to be right here in my c if I'm replacing my x's with zeros. So my y-intercept, without having to do any work, is just the point 0, comma 14. Okay. So now I'm going to let you do letter E, which is the same idea, similar ideas to the previous two. And we'll see, and then we will move